One of the things that students often want is a plan for working problems, like a this is how you work physics problems. And I think what they want is a very specific, like use this equation and then use this equation. And that doesn't really exist, but there is sort of a problem solving framework that you can use for all physics problems. And we're going to really start using it on these Newton's law problems now. So I'm going to give you guys the framework, give credit to the people who developed it, and then we're going to use that framework applied to a problem, and then we'll use that same framework for all of our sample problems. You don't have to submit these different steps to me at any time, but if you think about all of your problems in this way and work through this framework, I think it'll really help. One of the things that you'll see with this framework is you don't really think about equations that much. Those kind of come later. You think about how all of these different ideas relate, and then you get to equations. So this is from the Cooperative Problem Solving in Physics User's Manual that was developed by Kenneth and Patricia Heller from the University of Minnesota. There's a link there if you want to see all of it. And they set this up actually as a framework for students doing group problem solving, cooperative groups, in their physics classes. But the same basic 5 steps work for any problem. And we're going to step through all 5 of these steps now. So they start with recognizing the problem and figuring out what's really going on in the problem, taking the word problem that you have and really figuring it out. They're then going to describe it in terms of physics. What does this have to do with the concepts we've been learning? How does this fit in? Plan a solution to get from where you are to where you want to be. Execute the plan, and then evaluate the solution. So here's our sample problem. Jim was texting while driving, which is a very, very bad idea. And because he was texting while driving, he accidentally ran off the road. When he looks up after sending his long text with like 17 different emoticons and lots of exclamation points, he's driving down a grassy hill. He's going 25 meters per second. There's a large tree that's 50 meters in front of him and lots of smaller trees on both sides. If he can stop in 50 meters, staying straight and stopping is his safest option because he won't hit anything. If not, he needs to go ahead and turn and just crash into one of the smaller trees and kind of take the hit and figure that it's safer to crash into that smaller tree than it is to hit the large one. He'd be hitting his brakes either way and slowing down some, but smaller trees safer than big trees. The force of friction between the tires and the grass after he hits the brakes is 5,145 newtons. And the mass of the car with Jim in it is 1,500 kilograms. So we want to figure out if Jim should stay straight, slam on the brakes, and he'll stop before the tree, or should he hit the brakes and then turn and just take his chances with one of the smaller trees. This is why you shouldn't text and drive. So step 1 is recognize the problem. And there are a few things you want to do during this step. One is you want to draw a picture. And I've drawn a lovely picture here on the side for you, where I have Jim's car. I have the distance from the car to the tree. I have the speed of the car, the slope of the hill, and a lot of the picture of what's going on. As you can see, your picture does not have to look good. My picture does not look good. I put a little color in it just so I wouldn't feel quite so bad, but your picture can be anything. But you want to make sure you can picture what's going on in the problem and sort of put that in real world. Next, we're going to draw a free body diagram. We're going to identify what we know and then identify what we're trying to figure out. So there's our picture. Now we're going to do a free body diagram. So here's our dot that is Jim and the car right here. Next, we know that the force of gravity will be acting because Jim's on Earth. So we'll add that. Then we know there's going to be a normal force from the ramp on Jim and the car. And that normal force is going to be perpendicular to the ramp. So we're going to draw that in. We're going to label our normal force and our force of gravity. We also know that when Jim applies the brake, there's going to be this friction force. And that friction force is going to act up the slope to try to stop the car. slightly more convincing F. So there's a pretty simple free body diagram, but I think I might want to modify it just a little bit. So I'm going to erase my force of gravity like this, because I want to break it into its components. So I want to say, I know there's a component of gravity going down the slope, and I'm going to let that be x, and a component of gravity going into the ramp. So I have FGX and FGY. I have the normal force and the force of friction. Now I want to figure out what I know. Well, because I know the mass, I know Fg is going to equal to 1,500 kilograms times 9.8 meters per second squared. I also know how to find Fgx and Fgy, because both of those are going to be found by resolving that vector. So Fgx equals Fg sine 20 degrees, Fgy, Fg cosine 20 degrees. And I also know, if I think about this, Jim is not accelerating off the ramp or into the ramp. So Fgy is going to also equal Fn. Okay, I know that, and really what I mean is it's going to equal the magnitude of Fn. I know that, and, well, I also kind of know what his velocity is initially, right at the start of this problem, and that's 25 meters per second. I also know that if we're kind of figuring out where he's going to stop, his final is going to be 0 meters per second. And what I don't know and what I'm looking for is the displacement. So I don't know that yet, and that's what I want to figure out. And I apologize for my chicken scratch looking handwriting on this. I'm still kind of getting used to this stylus, but hopefully you guys can read it, and please let me know if you can't. Okay, so we've done step 1. Now we're on to step 2. We want to describe the problem in terms of the field. So we want to talk about this problem kind of in physics talk. We want to talk about, is there constant acceleration? Is there a projectile? Can I talk about net forces? What can I talk about in terms of this problem? And so how I would say is we need to figure out if the displacement the car will undergo while stopping is greater than 50 meters. The force and mass are both constant. Mass, not maths. The force and mass are both constant. And we know the acceleration will also be constant because force and mass are constant. So we have a constant acceleration problem. Really, we should figure out what that acceleration is. To do that, we're going to plan a solution. We're going to sketch a path from what we know to what we want to find out. So in the end, we want to find out the displacement. We have our free body diagram, and from that free body diagram, if we let down the ramp be positive x, we know that the sum of the forces in x, so F net x, is equal to the force of friction plus the force of gravity in x. We also know that that F net x is going to equal to the mass of the car times the acceleration of the car. And I need to go ahead and label some of these as vectors by giving them their arrows. Once I know that acceleration, I can treat this as a constant acceleration problem. And I then can relate acceleration, v initial, and v final, and use those to get displacement. So now I have a path from things that I know, like the force of friction and the force of gravity in x, to what I need to know. Now we're going to execute the plan that we made. So basically we're going to plug and chug. We're going to put numbers in to what we've decided was our plan and work from there. So the first thing we're going to do is figure out F net X. And we said that's equal to the force of friction, which we said was 5,145 newtons. And that's up the ramp. So that's in our negative X direction. So we're going to give it a negative sign. So fix that 5 a little bit. I just made it worse. There we go. Acting down the ramp, we have the force of gravity in the X direction. So that's going to be 1,500 kilograms times 9.8 meters per second squared times the sine of 20 degrees. So I'm going to take a minute and plug and chug and figure out what that gives me. So 1,500 times 9.8 times 20 sine gives me 5,027, 28 when you round it. So then I'm going to subtract 5,145, and I get that F net X equals negative 117.3 newtons. One thing you may ask is why this isn't negative. We set down the ramp as the positive sign, and so that's acting in the positive X direction, so we don't need a negative there. So now we have F net in X. We also know that's going to equal to the mass times the acceleration. So I can say negative 117.3 newtons equals 1,500 kilograms times A. Plug and chug again. So I'm going to divide 117.3 by 1,500. And I get that A equals negative 0.078 meters per second squared. So newtons are kilograms times meter per second squared. So when I divide by kilograms, I get meter per second squared. Now I need to use this acceleration that I have in one of my constant acceleration equations to find the displacement. So I don't know time yet, but I know V initial and V final. So take a look and figure out what equation could I use to relate those terms. So I looked up my constant acceleration equations and I found one that relates all of the variables that I want to be able to relate. So now I'm going to plug and chug. So V final, 0 meters per second squared equals my V initial was 25 meters per second, and that was going in the positive X direction, plus 2 times my acceleration, negative 0.078 meters per second squared, times that displacement, which is what I want to find. So I'm going to add this whole term over to the other side. So that negative is going to go away. So I get 2 times 0.078 meters per second squared times x minus x of 0 equals 25 meters per second. And that whole term is squared. And then I'm going to divide both sides of the equation by this. And then I'm going to plug and chug. So 25 squared gives me 625. And when I work through, I get that x minus x sub 0 is 4,006 meters. So Jim does not have any chance of stopping before he reaches the tree. Okay, so does our solution make sense? Well, we have a really steep hill. And so the difference between the force pulling Jim down the hill, that force of gravity, and the force trying to slow down his movement is pretty small. And our mass is fairly big. So if we think through, our difference is small, our mass is big, so our acceleration is really little. And if we have a really little acceleration and a pretty high initial speed, it seems to make sense that it would take that long. We could also take that distance and plug it back in and maybe find the acceleration that would be needed, or find a time and then work backwards through the problem to make sure it makes sense. But in general, at this step, you want to look and say, does this solution make sense? 4 kilometers to stop is a really long way. So on the surface, it seems like this answer doesn't really make sense. In reality, it's probably just that the problem doesn't make as much sense, because that hill is pretty steep. A 20-degree hill is much bigger than what you're going to find on a regular roadway. So it might make sense that your brakes might not be very effective on that hill. Jim, however, is no longer on the road because he drove off the road. So maybe he found a 20-degree hill. So you just want to take a minute, think about your solution, and try to see, do I buy this at all? And in this case, I would say that I do. At first, it doesn't seem probable, but then when I think through the rest of it, I think it makes sense.